contribute to the answering of that question. So just because this is a unique field, like the opportunity to ask, what's your conception of a digital twin? Everyone has a kind of variety of backgrounds here.
I have a conception that it's a buzzword.
Absolutely. And why what's the tell me your arc on buzzword versus something of a word of substance.
Of substance? Well, it can be used for marketing materials, and it often is for almost anything that represents anything else.
It's like it's completely it's so widespread that it's like it's a meaningless term.
Yeah, it's almost a meme. And I apologize because there's probably many who don't want that to be.
Lots of marketers, certainly.
Yeah.
So my background, I've worked for instrumentation and hydrogeology companies my entire career. Worked in GIS my entire career. Also, significant work with graduate studies in remote sensing. So radar and LiDAR. I'm going to talk to you about two projects today. One LiDAR, one radar. My project on the radar side, and then a really fun project that's not my work, but is too good of an example of what digitization of our world allows us to answer questions. But like I'm in the same boat. Like the company that bought one of the IoT startup companies I was working for was Bentley Systems. You guys all familiar with different versions of Bentley? They scooped up a ton of IoT companies at once. We were one of them with this digital twin initiative, and it is very, very buzzwordy and almost meaningless. But there is a part of it that like gets back to a thing that I think that we're all striving for, which is interoperability, extensibility, the ability to respond to emergent situations. So the fire talk that we were hearing earlier today, like you have to have a functional system that's you're actually capable of participating, as well as historic references. So data records that stretch back
to 19th century,
70 years.
19th century even, yeah.
Yeah.
And that's nothing compared to Europe,
Yeah, well, and that capability is like we're on this one slice of we're digitizing things, but what'll be the next 50 years of questions of somebody saying nobody filled out the metadata in the 2000s because that's a ridiculous thing to do, but it'll be the thing that they're like, man, they'll find that one trove that someone has filled out all of the metadata and be like, we can answer so many questions now because things that we can't anticipate as workers in the space will become valuable. One of my favorite examples is I was at CU Boulder for geology. They have the air topo, air photo collection library in the basement of the Earth Sciences library there. And as a landslide geologist, we get to go back into the archives and we would find these air photos of different places. There's dozens of landslide sites in Colorado that I've been a part of investigating, but you could find an air photo that has attribution of the camera that it was taken, the conditions, the date, and you can start to like register that digitally and then use it as part of a historical analysis. So I've done that for Quebec landslide, for Heaney landslide, for Paonia landslide, the Muddy Creek landslide that I worked on for my PhD. And I just think that recognizing that we're a part of a longer arc of workers that will all be in this space, and like what are we passing on to the future generations of people that will take over our positions when we retire, and are we leaving little nuggets of troves of information that will be valuable to them or not. And I think that that's actually what, if there is substance to the digital twin initiative, that's what our calling is what can we create as a gesture towards that future work that, yeah, we all will do the work that we need to do to get done here, but are we able to invest, as Nathan put it, a little bit of extra effort into that library science to make it more valuable in years to come. So that one falls close to my heart. The two projects I want to tell you about today, we're going to learn a little bit about. We learned a lot about LiDAR yesterday. We went up into the cave and scanned the inside of Fulford Cave with LiDAR. So I'm going to go over a little bit on that and a really fun project. So I'll end on the LiDAR project. But the other one I'm going to tell you about, which has to do with my PhD work, which prepare your eyes to roll back in your head right now. Terrestrial interferometry of slow-moving landslides.
Oh, that's great. So you put a lot of sticks in the ground, right?
Variety. Some of them being radar signal sticks is more like it.
Okay.
So interferometry, does anybody hear that term and just it's like glaze over in their head of what that means?
Can you define it?
Yeah, so sorry.
Or eat some cantaloupe?
We're
Blackberries?
gonna do some blackberry science here.
Great.
Who has a watch?
Well,
Put on the stopwatch.
there's a timer on the...
Oh, even better. That would work. Okay, so LiDAR works with time of flight, right? So when I'm a transmitter and I emit, and then it is reflected back at me, there's
Good
a
catch.
time of flight. That's a photon, right? Photon or a radio signal, whatever you like to consider. And by measuring that, I can find out. Okay, another measurement. Let's actually do it. So, I emit when I throw this. Someone start the watch. Absorption.
That is a good example.
It does happen.
You lose some of
Good to
them.
know. Good to know. Let's see if we can get a reflective surface here.
Ooh,
All right. So I received it.
3.4 seconds.
3.4 seconds. So if we knew how fast I threw it, we know we can solve for the distance. Right? And that's what LiDAR does. Is it's a time of flight sensor based off of the speed of light of those photons.
We know the speed.
And we know the speed. It happens to be universal. Do you know the other information that this photon carries besides when it reaches?
Frequency?
It's close to the frequency.
Hmm.
Well, this does have a frequency of light.
And that
Right.
frequency might change in reflection?
Wavelength?
The wavelength. Let's assume the wavelength doesn't change. That it comes back the same wavelength.
And there's no absorption.
There's no absorption.
Then what else
One
can we know?
more. There's the brightness, right? Amplitude.
Entanglement? No.
We're getting a little closer. We can monitor the phase
Okay.
of where. So if I emit it here, it's a little sinusoid, right?
Where
So
on the wavelength it started? Where on the
it's
wavelength?
going, and it has its wavelength. It reflects off of the reflective surface,
And it has a wavelength.
and it comes back to me somewhere on the phase.
So you have like a 15.789 waves or whatever.
Yeah, radar waves are typically
Large number.
8 centimeters, 1.5 centimeters.
So a very large number.
They can be typically in INSAR applications, which this is interferometry that you're talking about, between 30 centimeters down to about 8 millimeters.
So are you basically talking about the distance along the wave that it's traveling as opposed to just that straight line?
That's right.
distance? Okay.
That's right. It's the
Where on the sign?
tracking how many, like where it returns in phase.
Yeah.
To me. So if I'm a radar sensor and I'm scanning and the scene is not moving, I scan and I get, it's an arbitrary, like wherever this blackberry comes into my phase measurement, it's an arbitrary thing. Sometimes it can be up here, sometimes it can be down here, but it's meaningless noise. I mean, it is technically a record of a very high precision record of the total flight distance of that.
Mhm.
But time is a much better metric for timing, time of
Distance.
flight and
Yeah.
distances. The fun part with interferometry, though, is that if you scoot back in your chair on the order of the same order of the wavelength, then when this comes back to me, it's not going to end up here at my phase measurement. It might end up right here. And I can actually take that as a ruler and map it onto how far you moved away from me. So it's a way of measuring very high
Small.
precision changes in position
Landscape.
from scene to scene to scene.
Small distance movement.
And like we're talking, we say that it's a gnat's ass because that's the level of precision. You can get sub-millimeter scale with lots and lots of measurements. And what's amazing about it to me, this entire technique was developed using satellites. So they were able to do that interferometry on repeat pass satellites. Some of the first interferometric pictures that were ever generated are
Beauty.
of earthquakes.
Oh.
So you would have an image taken, a radar image taken over a plot of Earth, and then there's a rupture of that earthquake, and then you see these fringes of interferometric phase difference, where the earthquake deformed the surface. Right in the center, it's decorrelated because it's such a big throw that you can't really count the number of fringes. But if you start from the outside, you get to actually count the number of fringes. That's the number of wavelength over 2, as it turns out, because it has to go back and forwards. But wavelength over 2, you have these like rulers that you can measure how much it deformed, and it revolutionized geoscience. It revolutionized the ability to monitor seismology, find out the strength, the impact, damage assessment of any given earthquake. We use it to monitor volcanoes today. We can see uplift. We use it to monitor the depression of groundwater aquifers as they are dewatered. And I got to use it to monitor landslides. So there's a number of situations here where we would have a landslide that would be, moving down slope. And you set up this radar and take measurements, and it's actively moving. This is not a landslide, for the record, everybody. So
Imagine, if you
but
will.
imagine that this is moving. Landslides can be cooking. They can be cooking at a meter a month. But with this high precision measurement technique, we can see things moving at millimeters a day, is what that translates to.
Can you also do this with avalanches?
Avalanches are tough because they're so fast moving.
Okay.
If there was slow movement, then technically you can see, and there's a lot of great snow science that's done with avalanches. It's more about the absorption of that snow than it is about tracking it.
I
How
imagine
do we worry
there's
about
also
the reflectivity? Yeah.
the snow itself throughout the heat cycle of the day has a lot of movement back and forth.
Completely.
That's unrelated to the
Like the overall
Expansion,
movement
contraction.
of the,
yeah. About like glacier.
Glaciers is one of the most beautiful examples because they're actually like 10 meters a day sometimes, and you can see the professor that I work with, Paco Gomez at the University of Missouri, Columbia, set up a tripod, and you have this amazing interference pattern where you can see it moving up here, see it moving further away down there, and he would always joke that he's like, you see the Doppler effect, like this glacier is literally going right, that noise that you hear when a motorcycle passes you is that you have tighter sound waves coming at you here, and then longer sound waves coming at you.
The farther they are away.
Yeah.
So
But
it
you
goes
can
down
see that
pitch.
in the radar pattern, and that's an amazing thing at that scale. So, the most, like, I'm a geologist, I'm a geoscientist, and being able to monitor landslides is certainly like the most interesting thing to me. One of the biggest projects in the third chapter of my dissertation was the chance. Do you guys remember anybody from the Seattle area?
From the West Coast.
Seattle has had a double-decker viaduct on the coast that went right into downtown. If you imagine these trees as downtown Seattle, there's this coast on Puget Sound with a double-decker, they call it the Alaska Way Viaduct, and it carved up into the middle of downtown. At some point, they decided they wanted to take that viaduct underground. And so they buried one of the largest tunnel boring machines ever constructed. It was 60 feet across. And they put that double-decker highway inside of a tunnel and dug it underneath downtown Seattle. One of the most ambitious projects ever undertaken. Problem was they hit they don't know exactly what it was, but it could have been like a metal well. It was some poorly accounted for, historic,
documented. Yeah.
Steel object that they ran into with the TBM. After about a mile and a half of progress, this thing was going to go fully 3 miles underneath downtown Seattle. So it immediately stopped, and they had to go replace the boring bits of TBM.
Yeah.
In order to do that, so if we just imagine roughly, this is nice because it's a double-decker highway, right? On this side, anything beyond me is Puget Sound, right? Inside here, you've got downtown Seattle in the trees. In this area here, it was an area called Pioneer Square, one of the oldest areas of Seattle. They say that the rock formations there are dead horses and sawdust because it's just trash that has like accumulated through flooding events. And there used to be, like, in downtown historic Seattle, there was a first floor, but at some point there were so many events and floods that they made the second floor the first floor, and that's like the resident road grade of downtown Seattle. So really terrible foundation material, highly movement. They had to dig through that to go create this rescue shaft for the TBM. And in order to do that, you have to pump out all of the water to create that rescue shaft.
Which
to create a center.
There's a lot of pressure on that water, I imagine.
So when you dewater an area, you drop the ground surface, and the downtown Seattle, that section of downtown Seattle settled about 2.5 inches over 9 days. This is 2014.
Must have been a lot of drywall cracking.
And
Foundations?
they're all lawyers' offices. And like some of the nicest, I mean, like Fraser Crane kind of lawyers' offices, like just a fancy part of downtown Seattle, right?
Could they not back out the drilling rig all the way back out?
No, they had to keep. It doesn't have a reverse. They built it without a reverse,
Oh.
so they couldn't back it out. And to keep going, they had to go
Clean it out.
I mean, this was at a tremendous cost and tremendous. It was a big snafu. I mean,
Millions, billions?
Absolutely billions. It was parked there for about 2. It was parked there for about 2 years, just not moving at all. And
So that's all your personnel, that's everybody.
completely. So they needed to monitor this settlement that was occurring. The dewatering kept going. They turned on the pumps and they didn't turn them off. But it became a question of all of the contracts were written that this TBM is intended to drill through and not disturb any of the utilities. Some of these utilities were wood-lined pipelines in downtown Seattle.
Mm-hmm.
We just found some of those in Glenwood, not in use, but
Yeah, like just
found them
Yep.
under Grand Avenue.
Like
Yep.
barrels that were transmission
Yeah.
pipelines.
Yeah, it was a bunch of barrels with like this metal wire around the outside. And it works like a keg. It swells up with the water and seals itself.
I mean,
So
you
is
know,
that
they
for
did what they
water, or-
Yeah.
did
Yeah.
with the
Yeah.
information that they had, right? And the materials that they had. So they were trying to measure it with total station circuits. So they would do continuous automated total station monitoring. They'd do a circuit, they'd try and close a loop. If you remember yesterday, we were talking about closing the loop. But the fuzz in the data was about 2 inches, and that was actually the drop. And the compliance was 1.5 inches. So I got to go in with that same interferometer. This is a tripod mounted device that I pointed at landslides usually, and put it up on a skyscraper in downtown Seattle and look down on Pioneer Square and try and measure the deformation over time. I'll give you a picture of what that looks like. This is the interferometer inside the radome. So it's a tripod mounted device or a pedestal mounted device, and it has 2 transmit antennas and or 1 transmit and 2 receives. Jenny knows what it looks like. And we mounted it on top of I'll just kind of out here, like it was on a tripod on the top looking down at downtown Seattle. Now this building, Smith Tower, it's this beautiful neoclassical building. It was one of the tallest skyscrapers built in like 1914. It had just had its 100-year anniversary. The reason that they couldn't build skyscrapers any taller than that at the time is that they were rigid structures and it was too rigid. Skyscrapers now, the ones in downtown Seattle, they sway. They're meant to sway. They accommodate that. But this one's actually pretty solid. So it was a great place. It was the only place that we could put our radar
Because then it wouldn't move.
and then monitor it to look at the deformation at the millimeter scale, sub-millimeter scale of this urban environment down below. So I had a LiDAR data set from 1998, Puget Sound LiDAR Consortium, early LiDAR contributors. They had meter pixel LiDAR, but downtown Seattle is moving all the time. So like in my LiDAR, I had the Kingdome represented from 1998, but the Kingdome has been demolished and they've built Century Field in downtown Seattle. So totally out of date, not like a high fidelity temporal digital twin. But I was able to construct viewshed analyses of basically like, can we cover the areas of interest and areas of concern before we go and deploy this radar? The lesson learned from that was that for as much information, as much time as we spent doing that, we put it in the place we thought we were going to put it, which is this Smith Tower spot. So it lasted for 8 weeks. The pumps had not turned off. We got some great data. We did get like diurnal shifts of every building that was moving with the temperature. We watched a parking garage that would get loaded during the day with cars and sink and then get unloaded on the weekends and come back up.
Pavement degradation? No.
Well, then it began. But we at intersections, specifically like at night, when there wasn't a lot of traffic, we were monitoring intersections where these utilities are known to be located, and we could take 2 or 3 of the persistent reflectors and monitor them over time. And I published those in my dissertation, and they are still decreasing as they're dewatering. But I created a headache for myself because all of the lawyers for the city, the contractor, the WashDOT, they all wanted different interpretations because they had potentially thousands of different lawsuits that could be levied against these groups. But we were measuring the gnat's ass movement of downtown Seattle from this skyscraper, and it was the best project of my dissertation, and really, really fun to be involved in.
Was it threshold? Sorry, got the number.
Yeah, 1.5 inches over. It blew through that threshold. I think they're still sorting it out on litigation. I sat on a couple of, they weren't really depositions, but just initial interviews, and it is a mess of politics. I felt like it was like in downtown Chicago, with sort of politics going down with the city of Seattle. So I think some of them are still pending. So that's radar interferometry. It's a really interesting and obscure method of measuring, but you can measure things at a very small scale that move millimeters per day. It really depends how fast you can scan it. So if you can scan it every 7 minutes, like one of these devices on a tripod, you're limited to the window that you can measure movement. But there are satellites going up all the time. We're about to, there's a consortium of the US and India called NISAR. And NISAR is going up, and we're going to get a lot more radar measurements very, very soon. So any questions about radar before I move on to the other fun LiDAR?
No, that's really cool though.
It's a really fun one. I've worked with the guys at the they're in downtown Glenwood, the River Water Conservation District.
Oh yeah, yeah.
So like
Colorado River District.
yeah, the Colorado River Water to measure Richard Dam.
Mhm.
They have a dam that's moving about an inch a year downstream and 2 inches settling. And so we've done measurements there where we're doing 6-month repeat passes. It's a really flexible one, but it's obscure, and I've gotten really good at trying to explain people like what its limitations and what its advantages are.
Pronouncing it, infrared. How do you say it?
So think interfere.
Okay.
Right? Because you're talking about the phases interfering with each other. So it's interferometry.
Interferometry.
So when you hear INSAR, that whole acronym is interferometric synthetic aperture radar.
Hmm.
And the synthetic aperture is, we're really splitting hairs, but it's just the camera that is creating the image. Either it's a moving image, and so they create it, or that device that I showed you is actually a real aperture radar. So that's
So-
your acronym.
So real aperture radar would be passive?
No, still can be active, but
Okay.
has to have an antenna
Okay.
of some sort.
Okay.
As opposed to creating an antenna by a moving object.
Okay.
Like a drone or a vehicle. Some of the most fun stuff, if you guys talk to me in 5 years, I'm going to talk to you about the vehicle-mounted, drone-mounted radar that's being done. Because that's just, there are different advantages and disadvantages depending on the wavelength. Okay, so for the next little project, this is going to be fun. Do we all know Roadrunner, Wile E. Coyote? This desert environment, the rocks that he would tip over. There is actually a scientific term for this in geology. It's called a precariously balanced rock, a PBR. And
Like balanced rock in Garden of the Gods.
like balanced rock and Garden of the Gods, anywhere where there are these, like, you have these cap rock, this rim rock that is highly resistant, and then the rock underneath,
Any
as soon as
pinnacle.
it gets hit by water, it starts eroding, and you get these beautiful pedestals of balanced rocks over time. So I want everybody to go find a rock, and we're going to create a balanced rock on top of this stump here.
Okay.
Size of rock are we looking for?
I think
That rock looks great.
I think whatever you can carry is probably worthwhile.
Yeah, you found one quick.
That one's good.
Is this iron am I looking at? Is this all red from iron or from something else?
Clay.
I don't know anything about geology. Not enough. Okay. We're balancing all the rocks.
Okay. Let's set this one on top of here because this will be more indicative. Okay, so there is a. Oh, you got a really good one. Okay, this is a.
Oh, that was great.
That one's good.
That's a great base
just
rock.
set that one there. Okay. Now the really exciting. This is the really exciting part.
Sorry.
Okay, so there is a group, a LiDAR group out of ASU, Dr. Ramon Aerosmith, and I'm sure that he has a professorship somewhere, but his grad student, David Haddad. And they took it upon themselves to, they had these terrestrial LiDAR scanners. Longer distance, Regal has measurement distances. The EZ400 was 400 meters. You can do things at 1,000 meters. Everybody has to wear funky sunglasses, but you can do large scale captures of radar. And they set out monitoring every single side of these balanced rocks on pedestals. So just imagine that same LiDAR device that we had, we can go capture in very high fidelity this particular balanced rock set. Why would anybody be interested in it? Besides, don't think like historical, don't think like that it's going to, Chuck Jones at Looney Tunes to do, real-time.
Well, safety.
So safety, it's a good question. We just saw that collapse of that stone arch in Lake Powell.
Mm-hmm.
So characterizing like when it's going to move. It's related to that, but it has nothing to do with safety. Erosion over time, absolutely, great. And I retract my statement. It has everything to do with safety, but not from that rock.
Well, it would be like any
Is it
kind of-
water? When landslides happen in water, there was a big one in Alaska, right? That killed a lot of people.
That's right. How did they know? How do they know how big the landslides in Alaska are?
Didn't they look at the trees that were picked up and then discarded on the tops of the mountains, or tops of the cliffs?
Well, and they even there are sediments of historical landslides pre-civilization of landslides, seiches that were 300 meters above. So there was a historical record. That's what this whole process of scanning all of these precariously balanced rocks ends up being related to, is that what David Haddad and Ramon Aerosmith were interested in is they were seismologists, they were paleo.
Oh, that is such a good demonstration.
I'm so sorry. That was not safety.
All good.
Okay.
The wind.
I saw it.
So
Was that planned?
that was not planned. I mean, right then, I am interested in the topple because for every pedestal balanced rock that exists, the other rocks that they scanned were boulders that were previously balanced rocks that have toppled over.
Okay.
And those are records of shaking events that have occurred in tens of millions of
Yeah.
years.
How often is this happening? How long is it happening?
You have a way of interpreting that if we have a balanced rock and it is precarious, and you can model, right, like you've captured the whole rock in high fidelity. You know the material properties. You know what sort of impulse of force it would take to knock it over, right? But you can model that as a ground shaking force as well. And there are precariously balanced rocks that would have fallen if there was an earthquake
Force.
of sufficient amount sometime in the previous 2 million years. But when you have those PBRs sitting, I wish I actually had a PBR beer here to demonstrate, because it's a nice cross acronym. When you have the PBRs sitting and they have remained balanced and undisturbed, you know that you haven't had an earthquake of a shaking magnitude in the previous record of paleoseismological history. Now, there are details that are modeled and get into heavy amounts. I'm sure David's committee was rife with questions of how quickly is it eroding, what are the limits of any paleoseismological interpretation, and lots of important things. Certainly, I'm not the one that can answer that, but I can just marvel at the fact that, like, by scanning these balanced rocks, you can reconstruct the history of earthquakes for a region, and then use that to inform the safety risk of the surrounding area as well. What is the recurrence interval? In Salt Lake City, there is, it's one of the highest seismic risks in the country because of the Wasatch Fault. But we have not seen an earthquake on the Wasatch Fault that would likely be the thing that would, if that goes, it is a very slow recurrence interval, but if that goes, it will likely destroy the city of Salt Lake, as it is now. So, but everything that's being built is now with a lot of seismic retrofitting, because they know that that is a possibility of that recurrence interval.
So you could potentially have two different landscapes that look similar and have a completely different duration or speed activity when it comes to PBRs.
Yeah, the size of the PBRs, how many of you can find and how many you can characterize, and then also looking at the ones that have fallen down. The intention of this demo was that we were all going to get up and
Jump?
create an earthquake and see if we could knock it down one at a time, because ultimately you get to, like, this earthquake wasn't big enough, but all of us bouncing was enough to topple it. That's what they're reconstructing.
Are they looking at occurrence like between the east coast of the U.S. and Europe, the coastlines, because they used to be joined, and
Yeah,
there's
there
different.
are global seismology records are. There is like a when we talk about the geoid, right? We all work with the geoid. That's because seismologists are really interested in the total shape of the Earth.
Yeah.
So there are models there. You can also you can see earthquakes from around the globe. They transmit through the mantle.
Yeah.
They don't transmit through liquid, so there's a bit of a shadow from every earthquake. But we will see earthquakes in Pakistan. They'll show up on seismograms all over the Earth.
Yeah.
And